By the way, yesterday I retained only up to first order derivative, but if you have non-minimal coupling, you will have second derivative. But then you can carry out the same exercise, but you have to do the integration by parts twice. Right. And then what we showed is that given any action for the matter field, what I am interested is do just a mathematical variation in the metric. We don't know whether metric is dynamical, whether it has anything to do with evolution, dynamical evolution of the geometry of the space-time, but it's a metric just to get me an action that is invariant under general coordinate transformation. Then what we saw is that if I make a variation in the metric, okay, so this is very important. You have to be very careful in understanding what I am saying. So variation in metric, arbitrary variation in metric, such that delta G mu nu, and I am assuming that the variation is such that at infinity, at both time infinity and space infinity, delta G mu nu variation is 0, okay, and this by definition, as I said, is G bar mu nu minus G mu nu. Under this variation, the action varies, and we got the result. So matter action variation is given by, so the definition in terms of energy momentum tensor, I always forget when is it plus, when is it minus. So plus when it is delta G mu nu downstairs, and then we also showed towards the end, this is same as minus 1 over Tc. Okay. Now someone will say that, look, this is a pure mathematical variation in a metric that only tells you how to write down an action that is invariant under general coordinate transformation, but the real matter fields, dynamical matter fields, are these phi a's and derivative of the phi a's. So you would have asked that if I want to derive the equation of motion for the matter fields, then I use the principle of least action. I said that the equation of motions, when the fields evolve according to the equations of motion, then the action is extremum. That means when the fields are evolving according to the equations of motion, if I make tiny variation, then to first orders in the variation in the matter fields, action must be, the variation in the action must be 0. Then you will get back your equations of motion. So if you do variation in the matter fields, phi a of x, that means delta phi a by definition is phi bar ax minus phi a of x. If phi so one should be very careful in underline the key things. If phi a of x is evolving according to the equation of motion and you made a tiny variation to phi bar a of x delta phi a, then principle of least action tells me that up to linear orders in delta phi a, the change in the matter action will be 0 because it's extremum. You're either at the maximum or minimum, so if you make tiny variation, there will be no change in the matter action. Here we are not demanding that here we didn't demand that delta m is 0, but here we will demand that under this variation, delta am is 0, and then we will get back the equation of motion, the dynamical equations of motion. So the two variations are different. This is called Euler-Lagrange equation of motion for the matter fields. Right. So with this, let us come to variation in the Einstein-Hilbert action. By the way, before I leave the matter, you see, we were wondering yesterday, and why should have this variation given you the energy momentum tensor? But there is a physical sense. I don't know whether Hilbert did the argument from what I am going to say, but I am sure Einstein would have done it. Einstein would have said that, look, what couples to gravity? In the case of electrodynamics, what couples to the electromagnetic field is the charge. So in EM theory, you have a Lagrangian density for the free electromagnetic field, which is minus 1 over 4 pi f nu f nu. You have a Lagrangian density for the charge field. For complex charge field, it will be half g mu nu phi star phi, etc. But the coupling between the electromagnetic field and the charge field, that coupling comes out if you demand gauge invariance. Then the coupling is the conserved Noether current J mu coupling with A mu. So the interaction term in the interaction Lagrangian density interaction is proportional to J mu A mu, where A mu is the vector potential for the electromagnetic fields. So Einstein would have argued that in the case of gravity, he is trying to find out a covariant theory of gravitational interaction. He would have said that the interaction Hamiltonian, after all, gravity is universal. What is the universal to all matter? Energy and momentum. Anything that doesn't have energy and momentum, they don't exist. I hope this is clear. Anything that doesn't have energy and momentum, we will never be able to perceive them. For us, it's a ghost world. And therefore, we can't talk about it. Why? Because any detection process, when I see you, there's an energy exchange between you and me, because the photons are falling on you, they are reflected from you, that means they are interacting and coming back to my eyes and entering the retina. So the interaction between objects, that's how we perceive, there has to be energy and momentum exchange. So therefore, anything that doesn't have energy and momentum, we will simply not perceive. They don't exist for us. And gravity being universal, it must couple to things which is universal themselves. And energy momentum tensor are universal. Energy momentum tensor exists for charged particles, neutral particles, weakly interacting particles, and what have you. And therefore, gravity, the interaction must be proportional to T mu nu G mu. I would guess that Einstein would have argued in this manner. And therefore, if you vary the metric, just like here, if you vary the metric, take the partial derivative with A mu, you will get J mu. Here, if you take the partial derivative of G mu nu, you should get T mu nu. But of course, it's much more complicated. Unlike electromagnetic case, it's not just that there's a root minus G sitting and there's a half factor sitting. All that comes out in a very nice manner in Hilbert's approach. I think that is the reason why Hilbert's method works. All right. So now let's come to the Einstein-Hilbert action. Which is for the gravity. So G stands for gravity or geometry, whatever you would like to. And R we know is same as G mu nu upstairs contracted with R mu nu downstairs. Okay. Are there any questions? Yes.
I'm not sure if I missed something that you said, but when do you put such an interaction? Is that when I want to study the back reaction of the matter on the background field?
No, we want to know what is the source of the field. Just like here, the source of electromagnetic field A mu is J mu. All right? I mean, go back to your Maxwell's equation. I mean, when you do the variation, what do you get? Your Maxwell's equation is in flat space time, F mu nu comma nu is proportional to 4 pi by C J mu. So the current density, the fourth current density, is the source of your electromagnetic fields. And Einstein would have thought that the source of gravity or geometry is the energy momentum tensor.
We actually never put such an interaction, that's what I'm saying.
Wow. Say that again.
I've never seen in field theory books.
This one?
Yeah.
Actually, no. In fact, that's the reason I thought of this, that Einstein probably, if you look at weak field approximation as to how the gravitational wave amplitude H mu nu interacts with matter, you will find even as late as a paper by Maulik, Parekh, Wilczek, where they talk about gravitational wave detectors detecting a stochastic gravitational wave background, you will find that they use, when they are doing path integral approach for the interaction of linearized quantum gravitational wave with quantum matter, you will find in their Hamiltonian, they use the coupling T mu nu, H mu nu, where H mu nu is the gravitational wave amplitude. In fact, when I remembered that this result, then I thought that that's how Einstein might have guessed.
That's why I was asking if this is to say that this is to study the back reaction of the matter on the classical field.
No, not back reaction of the matter on the classical field.
When we do ordinary field theories, we take that the classical field is not affected by the test particle or the matter field. So that is the reason we don't put such a term, T mu nu G mu nu.
Yeah, but as long as you are doing test particles, you are not interested in knowing what is the source of your background field. But here we are interested in what is the source of the field. Okay? All right? Yeah. Correct. So let's go ahead and ask ourselves that, look here, now metric is no longer a kinematical quantity that has been introduced just to get an action that is invariant under general coordinate transformation. Now Einstein comes and tells that the metric is a dynamical quantity itself. And I mean, in physics, when we say something is dynamical, that means for it you have to write down an action. And to get the equation of motion, just like for the equation of motion of matter field, what we say is you vary the matter fields and demand that the action for the matter field be an extremum. Therefore, when you vary by tiny amount, delta m must be 0 up to first order in the variation, and you get your dynamical equation for the matter field. Now we should do the same thing. We should vary the metric and get the equations of motion for the dynamical field. But metric is not only appearing in the Einstein-Hilbert action, metric is also appearing in the matter action. So therefore, the total action, full action, is the matter action plus the action of the geometry or the gravity. And now we will say the equation of motion for the geometry. I am not interested at the moment equation of motion for the matter. So therefore, I will say therefore equations of motion for G mu nu must arise by demanding the full action delta A is 0 under okay. We have already seen how the matter action varies under G mu nu. Now we will do the same for this. So we will say delta A of G. Now we are varying with respect to the G mu nu. Delta of this, wherever G mu nu appears, all right. So delta of Leibniz, so Leibniz rule appears here too. There will be a term which is G mu nu, R mu nu, delta of root minus G. Okay. Then plus delta of G mu nu, R mu nu, root minus G, plus delta of R mu nu okay. Right. Okay. Now let me first consider this. I'll quote a result. It's a well-known result. If you want the derivation of that result, I'll give you the hint. It follows from a very important matrix identity, which normally when we learn matrix algebra, we don't learn it. And I first saw it in Weinberg's book, and it's a very important matrix identity. Let me anyway give that matrix identity, because it's such a useful result. Normally when we learn matrices, we are never talked about this result. Supposing your M is a n cross n matrix. It's a useful result. So I am giving this because in some other context you might need it. Then the result is this. Trace of natural logarithm of this matrix is equal to natural log of determinant of the matrix. This is a matrix identity. And if you use this matrix identity, you can prove that variation in the determinant of the metric. What is small g? G is by definition determinant of treating the covariant G mu nu as a matrix. Then this, I always forget which is plus and which is minus, so let me, so plus G, G mu nu, delta G mu nu. And obviously, if variation in the determinant of G is G, G mu nu, G mu nu, this is the same as minus G, G mu nu, delta G mu nu. Why? Because again, yesterday also we used the fact that because G mu alpha, G alpha nu is Kronecker delta, so therefore this minus so now, I mean, if you therefore set mu to be beta, you get back this result. Okay. And because we are using delta G mu nu upstairs, everything is upstairs, so I'll use this part. I'll not use this. So we are interested in del of root minus G. So del of root minus G, I always go from first principles in order that I don't make mistake. So therefore this can be written as del by del G of root minus G. It's a slow process, but I don't like committing mistakes and retrace my step. Okay. And this is nothing but del is square root, so half minus G, and because minus and del G by del G mu nu from here is del G by del G mu nu from this equation is simply minus G G mu nu. So minus G G mu nu del G by del G mu nu minus G G mu nu del G. And therefore minus G by square root of minus G is square root of minus G, so minus half square root of minus G G mu nu delta G mu nu. Okay. So del root minus G, we have derived the expression, so let us put this here. Remember, G mu nu R mu nu is same as R, so I get minus half R root minus G G mu nu. So let's see, R has come from that and del root minus G, so minus half, okay, minus half and root minus G G mu nu del G mu nu. Then this is there anyway, plus R mu nu minus root G, this one, R mu nu, the second term, R mu nu minus root G delta G mu nu. Okay. And then finally, the last term, which is delta R mu nu G mu nu root minus G. Is there any question? What?
Yeah, the bottom line. There are two minus signs, so it should be plus half.
Here? No. Be careful. See, there is a square root of minus G in the denominator. There is a minus G in the numerator. Minus G by minus root G is minus root G. and this minus half remains minus half. Is that clear? Okay. So one should be careful. So this is correct. Okay, now let's look at this term. By the way, I mean, since I have done this, might as well go one line and get a neat result. Delta G mu nu is common to delta G mu nu, root minus G is common to root minus G, and then you can see that this is nothing but R mu nu minus half R G mu nu into delta G mu nu into root minus G. There is nothing but the Einstein tensor. Plus, so this and this I have combined, R mu nu, root minus G, G mu nu I have taken common, minus half R G mu nu I have taken common, and this final term delta R mu nu. Okay. Now let's go back to the expression for R mu nu. R mu nu by definition is take the Riemann curvature tensor and contract the top index with the second index. That is our convention. Some people put it with a negative sign, but so there, when you do that, there will be a negative sign for the Einstein equation overall. And this by definition, Riemann tensor we have seen, so alpha mu, when I have taken alpha, there is a nu here, then alpha mu, this is anti-symmetry thing, so it will be alpha nu, and there will be indices. I am at the moment not interested because I will use that same trick, so that I will go to a local inertial frame. Okay, so okay, variation, we are talking of variation. So delta of R mu nu. What is our variation? Our variation is variation in the metric tensor. That means so basically I am saying that you use the G bar metric. By definition, this is R mu nu of G bar minus R mu nu using the metric G, and therefore there will be a term del by del x alpha of gamma bar alpha mu nu minus del by del x alpha of gamma alpha mu nu. So the variation will be in the Christoffel symbol. Okay, I hope this part is. So if you write down step by step, you will never make mistake. That's the approach I take. It's slow process, but if you go step by step logically, you will never make a mistake. So this is same as delta of del x alpha of variation in the Christoffel symbol plus there will be a term del gamma plus gamma del gamma coming from this. Then there will be another term which is minus del gamma plus. I am not putting the indices here because you will see we will use the Ladau-Lifshitz kind of argument. Okay. All right. Now, what is the Landau-Lifshitz argument? That you can always go to a local inertial frame, but before that I must tell, remember these are all in the integral sign. So we will say that look, we are integrating over 4 volume element. So I am integrating, so take one 4 volume element, it is integrated over entire space time, Consider one small 4-volume element. In the small 4-volume element, delta r mu nu into g mu nu into root minus g d4x, it's a scalar. So it doesn't matter in which frame I am evaluating this quantity. So one should be very, very careful when you, now I am not trying to find out the local inertial frame application at one point. I am saying that this is an integral, the variation of this is an integral. And so integral is summation over all the various small d4x volume element. I choose one small volume element. And I want to calculate over the small volume element this quantity. Delta r mu nu multiplied by g mu nu multiplied by root minus g d4x. Root minus g d4x is a scalar. And so is delta r mu nu into g mu nu. It's a scalar quantity. So it doesn't matter in which frame I evaluate. And I will evaluate it in the local inertial frame. But of course, this is a whole integral. There will be another volume element, another volume element. Here, d4x prime. What do I do? But that's another volume element. There also I will use another local inertial frame. It's a scalar quantity. It doesn't matter in which frame I evaluate. And then sum over. It's a beautiful argument. That's the whole point. Einsteinian equivalence principle is a physical principle, but it's so useful. It simplifies calculations. So therefore, when I do that, I am not going to bother about these terms at all. So for me, delta r mu nu g mu nu this term, last term, this quantity, because I am using local inertial frame, I am not bothered about this. So therefore, this quantity. And in the local inertial frame, what has happened to g mu nu? So in the LIF, local inertial frame, this has become eta mu nu. So therefore, I have the result that del by, so local inertial frame, I am using the convention of Weinberg. So xi alpha, delta, it's a delta gamma, it's not gamma. Gamma at one point would have been 0, it's a variation, delta gamma alpha mu nu minus delta of del xi nu of delta of gamma alpha mu alpha. Let's see, all the indices are correct. So del by del xi alpha of delta gamma alpha mu nu minus del by del xi nu of delta gamma alpha mu alpha, and multiplied by g mu nu means in the local inertial frame it is multiplied by eta mu nu. Okay. Now yesterday, okay, but before I do that, remember, yeah, so I should first evaluate that because there's a gamma alpha mu alpha term coming in. Should I do it now or should I defer it? Anyway, let's first do it. Yeah. That you have done that, yeah, that expression. Anyway, let me first take it inside. Eta mu nu can be taken inside, it's a constant thing. So this becomes del by del xi alpha of eta mu nu minus, there's something I should have mentioned, but yeah, now is high time I'll mention that, but let me first write down. Eta mu nu has gone. See, tensor calculus is not difficult, but you have to be patient and see that you don't make errors in putting the indices Where there are too many indices, you can always make an error. So one just has to be careful. So let's see whether I have put in everything correctly. Del by del xi alpha, del gamma alpha mu nu into eta mu nu minus del by del xi nu, eta mu nu, del gamma alpha mu alpha. Okay. Now note that, our first problem set before the school began, there was a problem where we showed that if you evaluate Christoffel symbol using a particular metric G bar and Christoffel symbol, don't do any coordinate transformation, use different metric, then this object transforms like a tensor. Why? Because the inhomogeneous term delta 2 x prime mu by del x prime alpha beta, that cancels from here to here. So it's a tensor. And what is this? This is delta gamma mu alpha beta. So therefore, these quantities, delta gamma alpha mu nu, delta gamma alpha mu alpha, they are tensors. That's something we have to be aware of. Now, because there is summation, this is a scalar, because mu nu indices have been summed over, this is just a scalar. So I want to take a overall derivative with respect to z alpha, so that I have this nu should be alpha, and nu is anyway being summed over. So I'll call first of all this alpha alpha by different index beta beta. And wherever I have nu, I'll call it alpha. After all, these are dummy indices. Okay? So therefore, I can take overall derivative delta xi alpha del by del xi alpha of eta mu nu del gamma alpha mu nu minus eta mu alpha del gamma beta mu beta. Correct. Okay. Now note certain things. In the flat space, first of all, I have argued that delta gamma alpha mu nu, delta gamma beta, they are tensors. Eta is in flat space, it's mu alpha upstairs. Huh? There is this tail was there, that's why it has come below, but it's upstairs, eta mu alpha. Del by del xi alpha partial derivative is a tensorial derivative in flat space time. Okay. Now I will say that this is like mu nu is being summed over, so this is like del by del xi alpha of a vector. I'll use Landau-Lifshitz. This is all given in Landau-Lifshitz. This object is a vector quantity, so I'll call it W alpha. Mu nu is being summed over mu. There's some index error. Some index error which has cropped in. Okay, so this was not alpha; it was mu. This is mu. This is correct. Yeah. So when I was copying it, I copied it incorrectly. So mu is being summed over. So therefore, this quantity eta mu nu delta gamma alpha mu nu minus eta mu alpha delta gamma, it's a Lorentz 4 vector W alpha. So in a local inertial coordinate system, delta r mu nu g mu nu, the scalar, is this quantity. Now I'll say in a general coordinate system, what is the general principle of general covariance? That if something you know that is true in a local inertial frame, when you want to write it down in a general coordinate system, partial derivatives must be covariant derivatives. Wherever you have Minkowski metric, it should be the usual curved spacetime metric. So in a general coordinate system, your delta r mu nu, g mu nu must be equal to covariant derivative with respect to alpha of W mu. Now what is your W mu? W mu in the general coordinate system, W mu, W alpha, not mu. I am using W alpha is in the general coordinate system is G mu nu upstairs, delta gamma alpha mu nu minus G mu alpha, and this is a valid tensor because delta gammas are tensors. Okay, all right. Now I'll have to erase some part of this part of the board. So what I finally achieved is that part of the integral, so delta r mu nu, g mu nu, the last piece, root minus g, d4x, now I am doing the full integral, can be written as w alpha semicolon alpha multiplied by root minus g into d4x. Okay, so the last piece, the rest of the piece is this. The last piece, integral over d4x, this has to be integrated. So let us expand what is the covariant derivative. So what is the covariant derivative with respect to beta? W alpha, this by definition is ordinary partial derivative with respect to beta. This is a contravariant vector, so gamma alpha, derivative with respect to beta, beta, and W sigma, sigma. And therefore, this implies that W alpha semicolon alpha is wherever beta you make it alpha. So this is del W alpha by del X alpha plus gamma alpha, wherever you have beta you make it alpha, gamma alpha sigma alpha W sigma. But as you have done the tutorial thing, we know that the same as gamma alpha sigma alpha is what? Del by del X sigma of log root minus g W sigma, W sigma. which is same as del W alpha by del X alpha. This is nothing but del root minus g with respect to del X alpha is 1 over root minus g, 1 over root minus g, del root minus g by del X sigma, W sigma. But this, what I can do is I can take 1 over root minus g common throughout. Then I have root minus g del W alpha by del X alpha plus del root minus g by del X sigma sigma. But sigma sigma is dummy variable. I could have called sigma as alpha itself. And this is nothing but 1 over root minus g del by del X alpha of root minus g W alpha. In other words, after all this rigmarole, I have finally achieved that W alpha semicolon alpha is simply 1 over root minus g del by del X alpha root minus g W alpha. Root minus g cancels, and this is an integral of del by del X alpha of root minus g W alpha integrated over the space-time volume, full space-time volume. What is W alpha? W alpha by definition is a 4 vector which is given in terms of the variation in the Christopher symbol, and variation in the metric at the infinity is 0. So the variation in the Christopher symbol at infinity is 0. So I use Gauss's theorem. Gauss's theorem tells me that this is a 4 volume integral. So this will be nothing but root minus g W alpha d sigma alpha, where d sigma alpha is the 3 hypersurface area element and alpha, and this over the infinite 3-dimensional boundary, the boundary, 3-dimensional boundary, where W alpha is 0. So therefore this whole quantity goes to 0. This whole thing is 0. Now here I'll make a remark. Remark is this, that it's a magic actually, that the fact remains that your Einstein-Hilbert action was essentially given in terms of the scalar curvature R, and scalar curvature R had second derivative of the metric, and whenever you have a normal Lagrangian density which has second derivative of the matter fields, when you do Euler-Lagrange equation, you get third derivative, and third derivative equations are bad for causality. I don't want to go into that. So physical equations, they normally have up to second derivatives. So one would have thought, oh, Einstein-Hilbert action, it contains second derivative of the metric. When you do the variation, you will get a differential equation having third order partial derivative of the metric, which is bad. But thing is, it doesn't happen. Why? Because all the third derivative, where is the third derivative coming? Del by del X alpha of del by gamma alpha mu nu. Gamma alpha mu nu, okay. So those third derivative terms have gone away into boundary and they have gone to 0. All right. So a magic happens. That Einstein-Hilbert action, when you do the variation, your differential equation. So, okay, I have not completed the result. So, all of these things have to be now put in together. Yeah. So now, so final, okay. So let us systematically put in everything. So what we have achieved is delta A of G, with all this calculation, what we have achieved is the variation in the geometric part of the action, delta r mu nu, that part has gone to 0, is simply r mu nu minus half r g mu nu delta g mu nu root minus g d4x. Okay. The other part we have shown that when you integrate over the entire space-time, it goes to 0 by virtue of Gauss's theorem. And, there's a minus c cube by 16 pi g outside. And we also know that delta A of m that we did yesterday, again I always forget when is it minus, when is it plus, because I am taking delta g mu nu upstairs. So I had written it down, but I had erased this. So let me again. My delta g mu nu upstairs. So this is minus 1 over 2c T mu nu delta g mu nu root minus g d4x. Okay. And therefore, the demand that the metric tensor, when it evolves with time, when you have the solution, when you make tiny excursions about the true evolution of the metric tensor, then tiny excursion should leave delta A is 0. So delta A is 0 means the final thing is I will sort of take common minus 1 over 2c common overall, minus 1 over 2c common overall, then I have integral T mu nu plus, because I have taken minus, is equal to delta. Okay, so therefore we have overall delta A. So 0 equal to delta A is equal to minus 1 over Tc T mu nu plus, because I have taken minus 1 over 2c common, C4 by 8 pi g. This is Einstein tensor capital G mu nu multiplied by all these quantity delta G mu nu root minus g d4x. So this must be equal to 0. But this is arbitrary delta G mu nu. Your excursions from the true evolution of the metric, delta G mu nu is arbitrary. If this equation has to hold good for arbitrary delta G mu nu at every space-time point, then this must be equal to 0 itself. So we have the Einstein equation that Einstein tensor G mu nu is minus 8 pi g by C4 T mu nu. By the way, I mean, here we have got the Einstein equation G mu nu minus 8 pi g C4. If you define your Ricci tensor R mu nu as minus R alpha, you will get a plus sign. So it doesn't, you have to be careful when you are looking at Einstein equation. What is your convention of defining the Ricci tensor? That becomes important. Okay? So we have got the celebrated Einstein equation from the variation of Einstein-Hilbert action, and many physicists agree that this is one of the most beautiful equations of nature. And I mean, of course, people say beauty lies in the eyes of the beholder, but there are certain objective statements regarding the beauty. The beauty here is that on one side you have matter, on the other side you have geometry. And the fact is that there is absolutely no new parameter which has been introduced. Okay? Absolutely no new parameter. Those who work in modified gravity or any other form of gravity will find that absolutely you can't do without introducing new parameters. So Einstein has created a theory where there is no new parameter, same Newtonian gravitational constant, same speed of zero rest mass particles in vacuum. He gets a theory which in weak field and slow moving particle limit produces Newton's gravity, tells that particles acted upon by gravity, they are just freely falling particle which is geodesics, and gravity is nothing but non-Euclidean geometry of the space-time. So lot of things are explained, starting with, as Anuj has shown, the tests of gravity. They were done within few years of the general relativity proposal, and yeah, I don't think any other new theory had such a success. So when in 1979 for electroweak theory proposal, which came in 1964, it had to wait for a long time for the verification of the neutral current prediction of electroweak theory. So therefore in 79, Weinberg, Salam and Glashow, they were awarded the Nobel Prize for electroweak theory. But during that time, I remember I was still a master's student, the particle physicists said that the Weinberg-Salam model is still not very beautiful. And they said, why? Because the parity non-conservation that that weak theories show, the parity non-conservation was put in by hand, because the left-handed neutrino and left-handed electrons, they transformed under SU2, while right-handed didn't. They were SU2 singlets. So that was put in by hand. On the other hand, in Einstein's GR, nothing seems to be put in by hand. It's just sheer, curvature space-time and the beauty of using the local inertial frame ideas. Yeah, so, okay, yeah.
Problem that is, if you choose the LEDs to like plus C, suppose you add a constant to that.
Cosmological constant. Yeah,
very good. Not cosmological constant. Usually we have a Lagrangian, that is the Fourier Lagrange equation of invalid, and we change the Lagrangian L prime to L plus C. Such thing is not, such a property is not found by the action of the gravitation, because of group of noise.
Yes, that is what gives to cosmological constant. Good that you pointed, that's what is the, okay. So I did this entire analysis.
Patrick, before that, here on the boundary, it is not only the delta G mu is set to 0, the first derivative of the variation is also set to 0. That's two different conditions, right?
No, because Christopher symbol has G mu upstairs. So Christopher symbol, gamma mu alpha beta, is half G mu sigma, G sigma alpha comma beta plus G sigma beta comma alpha. what is this, beta comma alpha minus g alpha beta comma sigma. So delta will have delta of this part multiplied by this, and also this into delta. Yeah, you need also the first derivative of the metric to be 0 at infinity. Yeah. Correct, you're right. No, that's okay, because when you are doing arbitrary variation, then you would demand that not only the variation in some quantity, variation in its derivative must also be 0. That's the same thing, by the way, one does. Wait a minute. I mean, look, it's like this. Delta, we had shown this earlier, delta of del G mu nu by del x alpha is same as del by del x alpha of del G mu nu. Okay. Now we are saying that yes, delta G mu nu is 0 at infinity, but if delta G mu nu is 0 at infinity, in the neighborhood, del by del x alpha of del G mu nu should also be 0. By the way, the same thing is done for getting the Euler-Lagrange equation by variation in the matter fields. You also demand that the first derivative of the matter fields must also go to 0. This same idea roughly. So, Vairoz, you think that in some cases you don't do that?
It would be like, in the normal Newtonian case, it's like putting the coordinate change is 0 and the velocity change is also 0. It's not just...
But in the case of normal Euler-Lagrange equation for a point particle, you don't take it to infinity, you take T1 to T2. And you say that when point particle mechanics T1 to T2, you impose the condition delta Q's at T1 is 0, delta Q's at T2 is 0. You don't say anything about the derivative. But here, on the other hand, we are having the infinite space, infinite time. So if the delta Q's are 0 at infinity, that means 0 at infinity, you would expect that derivatives are also 0 because they are smooth at infinity. Yeah. Yeah, okay, so I shouldn't, there's still time, but yeah, let's talk about now cosmological constant. As one knows from historical point of view that Einstein knew one of the failures of Newton. Newton, with his theory of gravity, he wanted to have a cosmological theory where he said that, well, the universe seems to be static. But in Newtonian days, what did people know about universe? They thought stars, and stars don't seem to be changing. So Newton thought that the entire universe is unchanging, and Newton said that, can I use my theory of gravity for having a static universe? And he said, okay, the universe is homogeneous and isotropic, seems like that, and no problem, you take any shell of matter, then this element of the shell, if you have infinite universe, this element of the shell, should it fall? He argued, no, it will not fall, because as many objects are attracting this side, there are that many symmetrically, that many attracting other side, meaning one element is symmetrically surrounded by other particles. So therefore, this object will not experience any gravitational attraction and you will have a static universe. Of course, Newton was a genius. He knew that there was a problem. The problem was instability. Is if you just disturb a little bit here, then if it disturbed in this direction, this will be attracted by more compared to this, because it's 1 over r square law. So immediately the whole thing will collapse. So static universe in Newtonian gravity model is unstable. Unstable solution has not much value in physics. Einstein knew about all these. Einstein said that perhaps his general theory of relativity will not have the same problem, that with his equations of motion, he will be able to generate a static universe. Remember, by 1916, people had not, still the universe appeared to be static. And when he did that, he found no, even his theory predicts unstable static universe. And Einstein, clever he is, he said, okay, let me introduce something else. He said that instead of g mu nu equal to 8 pi g minus 8 pi g, by the way, minus etc., as I said, it depends upon your convention of the Ricci tensor. So instead of that, let me say that, okay, let me be careful. Let me use the way I got the equation, minus 8 pi g, there's a negative sign. Okay. So, he said, can I have a repulsive, cosmic repulsive term? He is being inventive. He is thinking out of box. No one has observed a cosmic repulsive term. That can I add something so that it will produce a pure repulsive term? Okay. And the pure repulsion, let me try to get that R mu nu, R00, 0. You have to figure out whether plus sign or minus sign. You figure it out, what sign it should be. So he said that let me add a term lambda g mu nu to the equation. Oh, by the way, I should have mentioned something else. Okay. So by the way, this equation is same as, you can raise the indices. I should have mentioned that. That's very important. Now note one beautiful thing. That's very beautiful actually. We have not talked about equation of motion for the matter field. Not at all. So far. We have only got the equation of motion for the geometry. But a strange thing happens. We know from Bianchi identity, this is true. I didn't show it, but you can show from Bianchi identity that Einstein tensor is divergence-less. That means g mu nu semicolon nu being summed over is 0. But if Einstein equation is true, then this implies that t mu nu semicolon nu is also 0. Okay? T mu nu semicolon nu equal to 0 is identical with local conservation of energy and momentum test. Local conservation, meaning if you locally see if energy and momentum is decreasing in a small volume element, there should be flux outwards. That is what is that is what is T mu nu semicolon nu equal to 0. Local conservation is there. Karthik asked me about global thing. When I do Killing vector, I'll show in general there is no globally conserved energy, globally conserved moment in general, only when there's a time like Killing vector. So after I do Killing vectors, I'll come back to global conservation. And as you can see that in a local inertial frame, you get T mu nu comma nu equal to 0, which is your standard result in flat space time. That local conservation of energy momentum tensor in flat space time is T mu nu comma nu equal to 0. You get back that by going into local inertial frame. Right. But the fact of the matter is, T mu nu semicolon nu equal to 0 is equation of state, equation of motion for the matter fields. I am not going to show it. T mu nu semicolon nu equal to 0 follows from equation of motion of the matter fields. Now that's very surprising that we obtained the dynamical equations of motion for the geometry, namely metric. We got an equation And from that equation, we automatically get the equation of motion for the matter. No matter what the forces are involved in matter field, matter equations of motion follow from Einstein-Hilbert, Einstein's equation of motion. That's very surprising. Okay, that's one thing. So sometimes, long time back, when I was a student, people were still trying to find out perhaps matter itself should be coming out of geometry. Wheeler had the big approach. Wheeler always wanted to say that there are no charged particles, there are only fields, and charged particle is due to strange geometry and topology. Charge without charge. You know, he said that if you have the two-dimensional analog, that if you have a sheet with hole connected, there's a topology which is genus 1. Then if there are electric fields entering and coming out, so here this is like positive charge, this is like negative charge. Okay, so you don't need charged particles. So he used the charge without charge, something without something. So when I was a postdoc here, I organized a quiz contest in the foundation day, which I called it quiz without quiz, inspired by Wheeler's charge without charge. Because my quiz questions were very funny quiz questions. They were not standard quiz questions. Anyway, that's a separate matter. So there was a move once upon a time to explain matter also in terms of geometry, because from geometry itself, matter equations are following. Okay. Now, Einstein realized that you can always add a term, a pure constant into g mu nu, which still maintains the energy momentum conservation. Why? Because you can write it upstairs. So g mu nu plus lambda g mu nu equal to minus 8 pi g C4. By the way, please figure out whether it should be plus or minus, because for repulsive, you need one of the signs. One would give you de Sitter universe, the other will give you anti-de Sitter universe. Okay? So you can raise the index. Now you see, if you take covariant derivative on both sides, g mu nu semicolon nu, lambda is a constant. If lambda is not a constant, what I am saying is not going to happen. If lambda is a constant, you will get lambda g mu nu semicolon nu plus minus 8 pi g by C4 T mu nu semicolon nu. But this is 0 due to Bianchi identity. This is 0. We have already argued that principle of equivalence demands that g mu nu's covariant derivative must be 0. So this is 0, and you get back local conservation of energy and momentum tensor. Now coming back to Vishnu's question, that yes, Einstein modified by adding a term, but can it come from the action principle? The answer is yes. That equation can be derived if you add another term to this, which is lambda root minus g d4x. If you do a variation, it's trivial, because now the variation is only root minus g, and we have done what is delta root minus g. You'll get back that equation. Trivial. But that question is still important. Adding lambda root minus g d4x extra term, where are you adding? Are you adding to the matter? Are you adding to the geometry? That is still an ambiguous thing. So what you said, that adding a constant to the Lagrangian density of the matter, but if something has been added to the overall action, where have you added? Have you added the constant to matter, or have you added the constant to the geometry? But I'll come, if tomorrow in the discussion part we get time, we'll talk about the 0-point energy of quantum fields and cosmological constant. These are all related. This all, the ambiguity, that C, where is it coming, is all related to that fact. This is the famous cosmological constant problem which still has not been answered. I mean, for a while string theorists thought that they will solve the problem of cosmological constant, but that has not happened as yet. Okay, what else did I want to state before I move to killing vectors? Anyway, whenever you get a question, you can ask me. Now I go to symmetries. So far, we have not talked about symmetries of space-time. Now I am going to talk about symmetries of space-time. Okay? So I'll erase this part of the board. Oh, by the way, I must mention, yeah, I'll come to your question. I'll just mention that later on, Einstein realized that his introducing this lambda term was a big blunder. He always said that it was the biggest blunder of my life. Why did he say that? Because he was hell-bent on getting a static solution. He realized, had he been more confident about his original equation of motion, he would have said that either the solution tells me a contracting universe or expanding universe. He would have predicted it, and after that Hubble, you remember Hubble observationally got the expanding universe only in 1929. By that time, George Lemaitre, around the same time when Friedman was giving the equations of motion for cosmology, George Lemaitre, a Belgian bishop, had not only got identical Friedman equations, but he actually predicted that the universe must be expanding. And that was, of course, in 1921 or 1922. But Einstein could have done that before, had he not been hell-bent on trying to produce a static universe. So that's why he said that introducing cosmological constant is a big blunder. But today we know there's not a blunder. Even today, the light curves of supernova type 1a tell us that the universe, the expansion rate, is increasing with time. That means a double dot is positive, and that a cosmological constant can explain. Of course, there are other problems with having a cosmological constant, namely the fine tuning. Why is it so small? So lambda came back. Lambda never disappeared. So in one of my articles I wrote lambda is like the Lewis Carroll's Cheshire cat, that the cat disappeared but the smile remained. Yeah, you had a question.
Just a historical question. I mean, when did this idea of Wheeler to geometrize these other particle parameters fail? When did it fail actually?
I have no idea. I am very bad at historical aspect, but the concepts, it excites my imagination and I will remember all that. But history details I forget. Yeah, okay. Now I'll go to geometry of space-time, yeah, and the symmetries. Okay, so given a space-time, meaning what? That you have chosen your coordinate system and you have solved the Einstein equations, meaning Einstein equations are second order differential equation in the metric, and given energy momentum tensor, initial value data, you have solved the Einstein equation, got the metric tensor for all times at all space. So this initial value problem, formulating Einstein's equation and in initial value problem, has been discussed thoroughly in Meissner-Thorn-Wheeler book. And therefore, if you know the metric after solving the Einstein equation, you can calculate Riemann tensor, Ricci tensor, and everything. So basically, G mu nu gives you the geometry of the space-time. Although curvature tensor gives you the true non-Euclidean geometry, but curvature tensor you can obtain if you know the metric everywhere by taking derivatives. Someone will ask that, look, in flat space-time, they were conserved quantities based on symmetries, like Noether theorem. Noether theorem says that if your Lagrangian density is invariant under some transformations of your matter fields, then there are conserved Noether current. And Amy Noether's work, her work was extremely important for field theory, and perhaps Hilbert was also inspired by that, and so on. So you would say that what about conservation quantities corresponding to symmetry when your space-time is curved? So then you have to say that how do I describe symmetry in curved space-time? So the one way to think about, perhaps there are more abstract way of thinking about symmetries in space-time, curved space-time, is that if you do something to the space-time and your geometrical quantities as functions don't change. That's very important. I'll highlight by giving the example. That is a symmetry. So very important. That function must not change the form when you make coordinate transformation. This is not same as values not changing. So there's a difference. So when do you say that, so you have chosen a coordinate system, given a coordinate system, your curvilinear coordinate system, x mu, you solve the Einstein equation, which will give you the metric tensor everywhere for all times. Now you want to know that this space-time for which I know metric tensor everywhere for all times, does it have a symmetry? Remember, we have done it all in one given coordinate system. So what kind of symmetry are we looking for? Space-time symmetry. You will say, okay, let me make just like Noether theorem. Noether did infinitesimal transformation. Let me do an infinitesimal coordinate transformation, arbitrary but infinitesimal, an infinitesimal but arbitrary coordinate transformation. So what you do is, you take your original coordinates x mu, original coordinates, infinitesimal means there's a parameter epsilon which is very tiny and a vector field. So let me call the vector field as chi mu of x. So chi mu is a arbitrary vector field. You can have any vector field that you choose. Is any differentiable, any smooth, infinitely differentiable, any smooth? We know, we have defined all these when we were doing differential geometry. Any smooth vector field. Okay? Obviously, under this infinitesimal coordinate transformation, your metric will transform. So I have to now see, do I take covariant metric or contravariant metric? Doesn't matter, we can always go from one to another. So let me take the covariant metric. Except that the transformation law, doesn't matter, we'll figure it out. This under the coordinate transformation will go to g prime mu nu of x prime which by definition is, that's the reason the coordinates will come below. That's why it was probably better to start with contravariant, but doesn't matter. We'll figure it out. By the way, sometimes when we do mathematics, we don't realize what physically this transformation means. These are all local. You know, at one hand, we are talking about old coordinates x, new coordinates, but what is the relation between this x and this x prime? Apart from the mathematical relation, of course, it is that you are doing all these at the same event. This, strictly speaking, is event-wise it is equal. It's not that this x corresponds to the coordinates of one event, this x corresponds to the event of another event. No. So tensor, these are all tensor results, they are defined event-wise, the same event. Okay. So we have got a coordinate transformation. The new metric is now a function of x prime coordinates. Old metric was a function of x. Yeah.
So here x prime and x are the same.
Yeah, so this x prime, this relation, okay, this relation is same event. This is defined at the same event. The argument x corresponds to the event p, and x prime is for that event. Okay, so but because 1 over delta x, you might say that how do I take the derivative del by del x prime below? So we can rewrite, that's why I was first wondering. So you can rewrite all these. You can say from this x mu can be written as x prime mu minus epsilon chi mu of x, but x is again the same thing, x prime minus epsilon of chi of, but you can do a Taylor expansion, but epsilon is very small. There I should have mentioned that epsilon is very tiny, where mod epsilon is much, much less than 1. So therefore, up to first order, the same as x prime mu minus epsilon chi mu of x prime itself, plus order epsilon square. I hope this is clear. See, remember, these are mathematical details, that x prime mu is related to x mu plus epsilon chi mu, which is a function of x. But when I take del by del x prime mu, I have to say how del x mu by del x prime alpha comes. So I have to rewrite everything in terms of x prime. But that's okay, because chi mu of x is same as chi mu of x prime minus epsilon, which is dependent on x, but x is x prime. If you do a Taylor expansion up to first order, this is true. Okay, convince yourself. When you do it, because these mathematical details are important to realize, that otherwise in some other case you might make a mistake which will give you completely wrong result. And hence, because we have del x alpha, etc., therefore del x alpha by del x prime mu is del x prime alpha, because remember, x alpha is x prime alpha, so del x prime alpha by del x prime mu minus epsilon del chi alpha by del x prime mu. And del x prime alpha by del x prime mu is what? Kronecker, because coordinates in the same frame are functionally independent of each other, and therefore this is Kronecker delta. Okay. So therefore, I know that g prime mu nu as a function of new coordinates x prime is same as del alpha mu multiplied by del alpha beta mu, del x beta by del beta nu minus epsilon.
Patrick,
Yeah.
can you do one thing?
Yeah.
Now onwards, instead of chi, can you use something else? Maybe psi or something.
Hmm?
That would be better.
What?
Instead of chi, if you use psi, it would be because x and chi.
But I am making it curly. No? The reason I didn't want to, I mean, standard books will use xi, but because I was using for the Lorentz coordinates xi a, someone might have confused that. But yeah, but I am making it curled, so it's not x, it's curl. It's chi. Okay? Well, but you know, you can figure it out, what is happening. Yeah. So del x beta, del nu minus epsilon, del chi beta by del x prime nu multiplied by g alpha beta of x. But small x is like chi. I understand your note. Yeah, okay. If you want, I can call it xi. Yeah, I can call it xi. So we can call this as xi mu. Okay, so let's now expand the bracket and simplify. So first term as it is, del mu, what is that? No, I have made an error. This is alpha. Now this, when I act on g alpha beta, beta contracting will give me g alpha nu of x minus epsilon del xi beta of del x prime nu of g alpha beta. Now I'll expand the whole bracket, but note epsilon is very tiny. I will retain only up to linear order. There will be a quadratic term, epsilon square, that I will neglect, because remember epsilon is very tiny. I am retaining only up to linear terms in epsilon. So this will become, first when it acts, wherever there is alpha you get mu, so it's g mu nu of x minus epsilon del xi alpha by del x prime mu acting on multiplied by g alpha nu of x. Then that coming here minus epsilon, so del alpha mu hitting this and alpha is being summed over, so it will be mu beta, so minus epsilon del xi beta of del x prime nu, but g alpha beta with delta alpha mu g beta nu. Alpha has become summed over g mu beta. And the final term is quadratic, so I will not. So this is valid up to linear order, so there are corrections which are quadratic. Now, what is the, so we pause, what have we got? We have got that the new metric as a function of x prime is old metric as a function of x, and we have this term. Agreed? Okay. But when I want a symmetry, what I mean is that the new metric as a function must be same as the old metric as a function. That means what I want is that if there is a symmetry, if this by this coordinate system is xi mu a vector field, when you do a space-time translation generated by this vector field xi mu, if it is generating a symmetry, then the new metric as a function must be identical with old metric as a function. That means what? That means g prime mu nu as a function of x must be same as g mu nu as a function of the same coordinates x if xi mu as a vector field generates space-time symmetry, if generates a space-time symmetry. Now this is very important, that when is a for example, let's go back to our classical mechanics. Why is 1 over r potential is rotationally symmetric? Because r is square root of x square plus y square plus z square. When you make a rotation, x's, y's, z can transform. But r, which is square root of x prime square plus y prime square plus z prime square, remains the same. So v of r as a function of r doesn't change. The function itself doesn't change. So therefore, if I want my xi mu vector field to generate a space-time symmetry, the new metric as a function must be same as the old metric. And that means g prime mu nu as a functional dependence, the arguments, if I take any argument, g prime mu nu of y must be g mu nu of y, or any argument. Okay, so this is very important. And therefore, before I do that, before I impose that condition, I must express g prime mu nu x prime, the x argument must be extracted. So therefore here itself, remember this equation. So now I will go backwards. Okay, I will go backwards and write Taylor expand g prime mu nu of x prime. So I will go backwards now. This can be written as, this is same as g prime mu nu of x prime is same as g prime mu nu of x minus, because x prime by itself is not minus now, x plus epsilon xi mu xi, and I make a Taylor expansion, so this same as g prime mu nu of x plus del g prime mu nu of del x alpha, and there is epsilon term, psi alpha. Everyone agrees with this? All I have done is done a Taylor expansion, because g prime mu nu of x prime. Now you see, now there is a x prime was the new coordinate of the same event, x is the new coordinate of the same event. So this is, I have added, so now it is no longer the same event, because I am interested in knowing the functional dependence of the metric. So therefore, this is g prime mu nu of x prime is same as g prime mu nu of x, and because I am making a Taylor expansion, therefore this is given by this. So I'll put back all that, and so what have I got? I have got the general result. I have not yet imposed symmetry. I have got the general result that g prime mu nu of x is equal to, and I'll take this term to the other side. This term, I'll take it to the other side. Up to first order in epsilon, I've got the equation to be g mu nu of x minus epsilon del xi alpha of del x prime mu of g alpha nu x Oh, by the way, epsilon I can take common, no? So why am I carrying the baggage of epsilon? So minus, I can take the whole epsilon common, minus epsilon del xi alpha by del x prime mu g alpha nu plus del xi beta but instead of saying beta, after all beta is a dummy variable, I might as well call it alpha. So del xi alpha by del x prime nu g mu nu now. G mu what? Alpha. Because beta I have called it alpha. So these two terms have been common. Now what has happened is I am taking this term Taylor expansion to the other side. It is minus, but because I have taken minus epsilon, so it will be plus. Plus del g prime mu nu by del x alpha xi alpha. By the way, this is a prime, no? Del g prime mu nu xi alpha. Okay. Any questions so far? Here there is no, the physics is here, but here there is no physics. I am just doing Taylor expansion. Now, the fact remains that g prime mu nu, okay, so g prime mu nu of x prime was this. So therefore, up to, remember there is a epsilon outside, up to first order, and I have a del g prime, where is that? Del g prime mu nu by del x alpha. So del g prime mu nu by del x alpha will be del g mu nu by del x alpha, and there will be second derivatives with epsilon, but there is a epsilon there. So up to first order, I can remove the prime. So I'll remove the prime. I hope you understand the logic. It is del g prime mu nu, but I put back for g prime mu nu this expression. So there will be del g mu nu by del x alpha, then derivatives of this with respect to x alpha, but all these are epsilon, and there is an epsilon sitting outside. There will be quadratic in epsilon. So up to linear orders in epsilon, I have this result. I hope this part is clear. But now you will say, oh, there are this del xi alpha by del x prime mu. Okay. I would like to, because everywhere everything is x, na? I would like to do something about it. Yes, let's do something about it. Let's find out what is del xi alpha by del x prime mu. This, by law of partial derivative chain rule, is same as del xi alpha by del x sigma by del x prime mu. which is same as, we have seen what is it? It is same as delta sigma mu minus epsilon del xi sigma by del x prime mu into del xi alpha by del x sigma. But this has an epsilon term, but there's epsilon sitting here. So the correction will be second order in epsilon. And if you take only the delta sigma mu, this is same as sigma sigma, the same as del xi alpha by del x mu and epsilon terms, minus epsilon term. I'm not writing the term, but when I put another term here, this epsilon will make it quadratic. So I'll just remove mu, because up to first order del xi alpha by del x prime mu is del xi alpha by del x prime mu. So I've removed the prime. You understood the logic? So we have to be consistent. I mean, that's the power of mathematics. We just have to pure logic and imposing that epsilon is so tiny that I can throw away second order terms in epsilon. So we have got a beautiful expression. That's g prime mu nu as a function of x's is g mu nu as a function of x and this term. Now it's not a tensor equation. You should not even bother about tensor equation. We are now talking about functional dependence on x. Now someone will say that can we express it in a way where it looks beautiful? It still doesn't look very beautiful, because mathematicians are always guided by beauty, elegance and brevity. I mean, they don't like so many terms appearing. And what is the guidance? The guidance is derivative of the metric is appearing. I should be able to use the Christopher symbols, because Christopher symbols are in terms of derivative of the metric, okay? All right. So, yeah. So let me, instead of writing too much, let me try to, what is the time? Because it's 1:40. I don't want to delay you guys. So I will, because I know the solution, I'll jump ahead and, okay, so let me give you the result, then I'll tell you why it is true. So the result is, this can be written as minus epsilon. The whole thing is nothing but covariant derivative of xi mu downstairs, nu, plus xi nu semicolon mu. The whole thing will get simplified to this. Okay. I'll now show that. Remember, xi alphas are vector field. So xi alpha is nothing but g alpha into sigma xi sigma. All right. Okay. So therefore, so I've given you the result. Now I will slowly, so that you don't get bored with the tedious calculations. So therefore, now I am starting here. I've already given the beautiful solution. I'm only showing why that solution is correct. So therefore, g prime mu nu of x will be g mu nu of x minus epsilon is outside. Del xi alpha by del x mu, remember, so this implies, I'll first write down del xi alpha by del x mu is same as del g alpha sigma by del x. There is It's a long algebra, but we can't help it. We have to do that. Del xi alpha by del x mu into g sigma plus g alpha sigma xi sigma comma partial derivative comma mu. This we know. So therefore, we have got the result that minus epsilon del xi alpha by del x mu is nothing but g alpha sigma comma ordinary partial derivative comma mu into g alpha nu, okay, g alpha nu, first term, then plus g alpha sigma, this term, times g alpha nu into sigma mu comma mu. This is first term. Second term is all I'll have to do is wherever there is mu, I change it to nu. Okay, remember, here it was alpha nu, it was mu alpha, but metric is symmetric. All I have to do is wherever there is nu, I'll make it mu, and wherever there is nu, I'll make it mu. But before I do that, let me see, at least this expression I have not made an error. Otherwise, the error will get propagated. Okay, so let me verify. I don't want to carry the baggage of errors. So let's see. Del xi alpha by del x mu. Xi alpha is g alpha sigma g sigma. Sigma is being raised. So therefore, del xi alpha by del x mu is del g alpha sigma with respect to x mu g sigma, then g alpha sigma sigma comma mu, which is same as g alpha sigma comma mu then into g alpha nu plus g alpha sigma g sigma mu into g alpha nu. I think I'm right. So and now all I'm for this term, I'll just interchange mu nu. So I get g alpha sigma comma nu g alpha mu plus g alpha sigma g alpha mu z sigma nu, okay, and finally this term plus g mu nu by del x alpha, but g alpha xi alpha is same as g alpha sigma chi sigma. Okay, now see some beautiful result. First of all, g alpha sigma alpha nu, alpha is being summed over, will give me what? This is Kronecker delta sigma nu. G alpha sigma, G alpha nu, alpha is being summed over, a Kronecker delta sigma nu, and sigma is being summed over will give me xi nu. So this is same as simply nu plus. Now come back here, alpha is being summed over, this is Kronecker's delta sigma mu. So sigma will become mu. Yeah, I'm hurrying up because we don't want to miss our lunch. Okay. Now, what about this derivative with respect to upper index? What do we do? There is another trick we will use. The trick is because g mu alpha g alpha nu is Kronecker delta mu nu, if I differentiate with respect to some other symbol, sigma let's say, or anything. So this means g mu alpha comma lambda g alpha nu is same as minus g mu alpha g alpha nu comma lambda, because Kronecker delta when I differentiate with respect to x lambda is 0, and therefore this must be true. G mu alpha comma lambda g alpha nu must be minus g mu alpha g alpha nu. But I want to express this in terms of, so I again multiply both sides. What is not being summed over? Nu is not being summed over. So therefore I multiply tau nu both sides. tau nu both sides. Tau nu both sides, nu being summed over is Kronecker delta tau alpha. So nu being summed over, so this Kronecker delta tau alpha, so alpha become tau. So this becomes, alpha has become tau. So we have got the result that g mu tau comma lambda is same as minus g mu alpha g tau nu g alpha nu comma lambda. Okay. So that means what? Upper derivative, the derivative of upper metric is nothing but with a minus sign you put in the tensorial properties. Okay. That's all. Okay. So therefore now we can use that result. This will come with negative sign. So minus, oh, I erased it. What was the term? I should have remembered the term. What was the term? Please tell me what was the derivative term here? Okay, I should guess it from here itself. It is mu. So probably it was g alpha sigma comma mu, right? Okay, this was the term. So let me be, if I hurry, I might make mistake. So let me write down explicitly. Make sure that this is what was, I erased it unnecessarily. So g alpha sigma comma mu is nothing but, there will be an overall minus sign because of that, and it will be g something something, doesn't matter, g alpha will be there, sigma will be there, lambda tau with respect to mu. That's what this equation means. Okay, so g alpha sigma lambda tau comma mu, and similarly this one g alpha sigma comma nu is same thing, g alpha lambda g sigma tau g lambda tau comma nu. So when you do that, you get the result that this is equal to g mu nu x minus epsilon. So there is a minus sign. So let's keep the minus sign as it is, minus g alpha lambda g sigma tau minus g alpha and sigma tau times, first I will write g alpha nu, then I'll write this g lambda tau comma mu. Okay, so this term has been taken into account. Then there is a xi nu, so xi nu comma mu, then this term minus g alpha sigma nu, which is minus g alpha lambda g sigma tau into g alpha mu, and then there is the other term minus what is the other term? The derivative term g lambda tau nu, g lambda tau comma nu, and then finally the final term, no, there are two more terms, xi mu comma nu and plus g mu nu comma alpha and g alpha sigma g sigma. I think I haven't made any mistakes. There are too many. I'll keep my fingers crossed. I don't think I have made any mistake. G mu nu comma alpha, g alpha sigma. Yeah. Now you see again a lot of simplifications happen. G alpha lambda, G alpha nu, alpha is being summed over. You'll get Kronecker delta lambda nu. So Kronecker delta lambda nu will make this lambda as nu. Of course, it's multiplied by G sigma tau. Similarly, come back here, G alpha mu, G lambda alpha, alpha alpha being summed over, Kronecker delta lambda mu, okay. So wherever there is lambda, it will be mu. Okay. And I have oh, by the way, there were zetas I have forgotten to include, because these derivatives had zetas, na? So there were zetas hanging. Due to some reason, I forgot to include the zetas. Yeah, so there was zeta sigma, right? There was a zeta sigma here. There was a zeta sigma here. And I had forgotten to include. So there's a zeta sigma. There's a zeta sigma. Note, this object, when I differentiated, there was a zeta sigma hanging. So those zeta sigma has to be, okay. Now, you see what has happened. I have now G sigma tau is here, G sigma tau is here, and this object I want to label alpha as tau. So alpha can be, this is a dummy index, I'll call it tau. Alpha is tau. So that I can take G tau sigma common. When I do that, and I'll take minus outside, G mu nu x, minus I'll take it outside, so plus, and G sigma tau outside, so G sigma tau also outside, and I've got the result that, oh, not only I can take G sigma tau outside, okay, let's be very, we shouldn't be hurrying, we will get G nu tau comma mu, this term, times xi sigma, but xi sigma is, I should have, here was it alpha or sigma? Sigma. Sure, no? Yeah. So, in this expression, G sigma tau has come out, and I have xi sigma here, and similarly, minus I have taken common, so plus G mu tau comma nu xi sigma. So this term has been taken into account, this term has been taken into account, and finally this term, because I have taken minus sign, so there will be overall minus sign here, and again I'll have G mu nu tau, G mu nu tau, and again xi sigma, but then there is also G mu nu, so I'll erase this, then there is a term xi mu nu plus xi nu. Now you can see that this object is Christoffel symbol, and you can expand this, you can expand it out in terms of Christoffel symbol, is exactly equal to this. So yes, this was not minus, this should have been plus. Okay, please simplify it, and because we are already crossed 130, this is a simpler thing. So we have got the result that in general, you do an infinitesimal coordinate transformation as a function, G prime mu nu as a function is G mu nu as that function plus this. But I don't want a symmetry. Symmetry means the function. So symmetry means G prime mu nu x must be G mu nu x. This means that xi mu is such a vector field that xi mu semicolon nu plus xi nu semicolon mu is 0. This is called the killing equation. That means the vector field xi mu generates a space-time symmetry provided it satisfies the killing equation xi mu semicolon nu, xi nu semicolon mu. Okay? Just do this simplification. You will see that if you expand this out, you will get back this result. Okay. This is ordinary mu. You'll get back because this is actually twice the Christoffel symbol. Is twice the Christoffel symbol. Okay? I'll stop here.